Well, welcome back from your little break. As you recall, this is our second major lecture on Fourier analysis, and we've been discussing discrete Fourier transforms, and we took a break last time just when we got to the part where we had to analyze, synthesize what we've done, and look at the real consequences. So if you look up here, look on your screen, you can see we got through all the way to function synthesis, and right in the middle of function synthesis is where we left off. Right there. Okay? So, what are the consequences of discreteness? So, if you look at this slide, slide number 36 on the bottom, you'll see that we have two equations here, and those are the equations we'll use. The first equation on the left is the equation for the discrete Fourier transform. And it's discrete in the sense that we only have a finite number of points, n points. We're not doing any double counting here. And we're summing over n values measured for the function, and we weight them with this complex exponential. So that's our definition of a discrete Fourier transform. And likewise, the inverse transform, or in other words, the function synthesis, how you synthesize the function, how you create it from the transform, is again a sum over the same number of values, capital N, but now we're summing over frequencies, omega sub n. Okay? And then there's a complex exponential with the other sign, and so forth. And okay? So we've seen that already. And so now below we see two sample figures. One on the left of the a Fourier transform, and one on the right of a function. Okay? So what we've seen already is that the spacing, the frequency interval, delta omega, is equal to omega 1, which is 2 pi over t, where t is the period, or which in this case is the total time of observation of the signal. Okay? And that's 2 pi over, and since we observe the function at equal time intervals, small h, nh, n is the number of observations we make, is equal to the period. So delta omega, omega 1, is equal to 2 pi over the period. And that period is really a period because, as we see here, a consequence of this formula, which is just the sum over sines and cosines, is that the function will always repeat itself on and on and on, and here too. Okay? So it's a periodic function, because sines and cosines are. And likewise, since we're summing over exponentials, the same kind of sines and cosines, complex exponentials, for the Fourier transform, that also repeats itself. So there's one repetition, there's the other. Okay? So that's one of the most obvious consequences of discreteness. The next consequence is that if we want to have a finer resolution here in the grid for omega, so here we have obviously discrete omegas, and they look jumpy. Well, they are jumpy. Sometimes they're jumpy because that's the mathematics, but whenever you do a discrete number of points, measurement points, it'll always be jumpy here. So if you want a finer interval, then you need to use a larger period, larger measuring period. So if we do that, we get a finer omega. And if we get a finer omega, then the Fourier transform will look smoother. Okay, so that's what you have to do. If you want a smoother omega, you want to measure it at lots of little points and have fine resolution there. Okay? But if you want delta omega to be small, that means the period has to be large. Fine. So how do you do that? Well, the best way of doing that is to take more measurements. No question about that. And measure for longer periods. One popular approach, and I have to mention it, is called padding. And that's where you say, okay, here is our measurement of our signal. If we assume the signal is 0 all the way to the beginning, and even, all the way out to the end, when we measure it, we put that in as the period. Okay, we put that in as our signal. So we add zeros to the signal. By doing that, you're not adding any new signal, but you're increasing the value of capital T, and therefore you're making delta omega smaller. Well, you can do that, but that raises this ethical question here in red, because it's a warning. You're actually then synthesizing data. You're making up data and mixing it with the data which you have observed. And then you have to always, I'd say, put that in as a warning. mention it someplace in your talk that you've synthesized some data. You've padded the data in order to get a smoother function. So the function itself, though, as best determined from the data that you've measured, you may want to show that and then show the smoother version. Because one of them is actually all you can deduce. The other is something you believe is correct, but maybe not scientifically ethical to add data points. Likewise, the synthetic function y of t, the one you've synthesized, will be bad at the points where it starts repeating. Now here with this transform, it's not so bad because we've already had a large zero. But once it starts growing again, which it's doing here, you can't believe that. So if you want a better function near the endpoints, again, you have to have larger periods. So one thing to do is to make the period larger, or measure out to infinity, and then you won't have a periodic function. Okay? There's another subject here, another consequence of discreteness known as aliasing and ghosts, which comes about because you've only made a finite number of measurements. And we'll talk about that in another little mini lecture shortly, actually. It's enough details here. Let's move on and see what the consequences are of this. And let's finish off our discussion of discrete Fourier transform. So take a look now at slide 45, please. Well, as I warned you way back when, we've had to go through a whole bunch of mathematics. It's not hard mathematics. It's just sines and cosines and complex exponential. But there's a lot of bookkeeping involved. But when we're done, we end up with the simplest formulas you could imagine. And now we see how we could do that by having a very concise notation and by using just one complex number, capital Z here. Okay. So we define capital Z to be e to the minus 2 pi I over n. And that's just, of course, cosine minus I sine, minus because there's a minus sign up there. And you see that capital Z depends on the number of data points, but has no units to it. And it's fairly universal. It has no dimensions. And you could just calculate it anytime you want. So, but it categorizes the experiment by the number of points measured. Okay? If we express the Fourier transform, capital Y, in terms of capital Z, we have this very simple formula. The Fourier transform is just some constant, again the sum, and it's just powers of Z. Z raised to the nk power, n being the nth value of the transform, k being some power which we sum over. And then likewise it's weighted by the transform itself. And if we take that one step further and say what is the function, or the synthesis, the function itself now is just a sum over, again, points, and again just powers of Z, in this case inverse powers of Z, which really are the same as powers. Okay? And likewise weighted by the transform. So these two formulas are just very interesting. They're very neat, they're very simple, and they can be computed quite easily. Before we go on to the computation, let's mention that you've probably seen, if you've taken a class in transformation theory, in rotations, you've studied that, symmetry operations, that this kind of a function is what you use to rotate a function, any arbitrary function, from one coordinate system to another, or to rotate the coordinate system from one frame to another, whatever. So that you can view here what a Fourier transform is as just a rotation of the signal you've measured into a new space, the Fourier transform space. Very nice, because that's all these Z's do. And likewise, you can say, oh, once we have the Fourier transform, this Z operation, raising it to power, just takes the transform and rotates it back into signal space. So in that way, you have a signal. Whether you're viewing it in signal space and time or frequency space, is just related by a rotation. So that's a very neat way of thinking what a Fourier transform does. In terms of computation, we realize that this power, nk, is not even that. You don't even have to raise Z to any power, because Z to the nth power times the kth power, you just multiply n by k, and you evaluate it when you evaluate the sines and the cosines. Okay? So it's just evaluating sines and cosines. And in fact, if you look at it, n is an integer, k is an integer, everything here is an integer. W, I have no idea where the W came from. Strike it, it shouldn't be there. N is an integer. Okay, so they're just integers, and so these values of the function that we value, the sines and cosine functions, all repeat. And that's the basis of a very improved algorithm known as a fast Fourier transform, because you just realize, oh, I'm just repeating the same number again and again, and sine and cosine is going to be periodic. So there's even more symmetry here than comes about from the trigonometric functions directly, but we won't get into that now. That'll, again, I promise you, that'll be another lecture, but it's sort of an optional lecture because it just gets into so much bookkeeping, and if you wanted to be an accountant, you could have gone to business school. But anyway, let's look at the next slide just for a moment. It's a very short one. We'll just talk about it for a sec. Now we'll just really talk about this slide. Maybe we need closure. Remember, we started off with a Fourier series. That's where Fourier's theorem came from. And that was a sum from 0 to infinity, an infinite number of sum of some constant times cosine n omega t. Now we recognize this constant a sub n, of course, is just the Fourier transform, or just the real part of the Fourier transform. And you can say, well, this DFT, though, we spoke about it as transforms. So how do we do DFT for a series? Well, you just do the transform. But anyway, let's say, we have here our function. We've measured it a discrete number of times. 0 and n correspond to the same measurement. So again, we are assuming that due to the finite number of measurement points, the function has to repeat over and over again. That's a way of making it easy. So the repeat period t is as before. We still can only deduce from n measurements n independent values of the constant a sub n. So we just use the trapezoid rule. A sub n is now equal to the sum over the capital N values that we've measured as before, just with cosine. And you can either evaluate this directly, or you can just do a DFT and just use the real part. And then we truncate the sum back to get what was the infinite Fourier series. Now it just becomes a finite series because we only have that many measurements, and they're all periodic anyway. So that's DFT for Fourier series. So it's essentially just do DFT for the integral. It's the same answer. Okay. So let's look at slide 56 at a code implementation, a sample way of implementing this. We have so many languages we can choose from. We can give you examples. Here, this is actually Python. So it's given on a DVD you can get, or the electronic version of the book, and called DFT complex.python. One of the nice things about Python is it actually has complex numbers built in. We've shown you in the textbook earlier how to do complex arithmetic with Java. Fortran also has complex arithmetic built in. So C doesn't. So C you have to do it yourself. So here, this code is Python. It's essentially identical to C or Java. Fortran would have the same structure, but it'd be a little bit different. What you see here is, there's just some constants up front. The number of points we're doing, 2 pi, which is just 2 times pi, etc., normalization. And here we're defining a function. So we just call this function to do a Fourier transform. You don't even have to do that. And what is it? It's just 2 sums. It's a sum first over n, one of the indices, and then it's a sum over k. Okay, so that's the double sum we had previously. Here we start off the sum at 0. It's a complex number. That's the real part. Imaginary part is 0. We're summing over the n values again. And we have z, which is just 0, 2 pi kn over capital N. That's just z. And then we're adding it to the sum plus equal, just add to it, times the signal times that function, and that's it. Okay? And then when we're done, we just normalize it with the square root of 2 pi. So it's just exactly what we said. It's just 2 finite sums. You evaluate it, and you're done with. Okay, so now it's time for you to do some work. So let's look at slide 57, and that's where you have to do your homework. Before we tell you exactly what to do, you shouldn't think of this just as an assignment. You should think of this as part of your tools. Whenever you do a Fourier transform on a computer, even if you're using a canned program, which most of you will be, but this time in life you should at least write your own, look inside the black box, see what's going on. So whatever program you use, always test it on a simple case, because you'll test it on sophisticated cases, but you're not sure what the answer is. So do something, an analytic case whose answer you know. So here's a simple analytic case we give you as an exercise. Equation 20 is a function, y of t, and it has 3 terms in it. Okay? And each one is a sine or a cosine, in this case a cosine. So we know there should be 3 frequencies. Oh, that's good. We know the frequencies should be in the ratio 1, 3 to 5. Okay? So there should be 3 frequencies spaced by 2, 2. They should be evenly spaced. And the strength should be, the strength should be the components we have out front. So the strength of the first frequency should be 3, second 2, the third 1. So the 3 Fourier transforms you get out should be evenly spaced, 2 omega, and they should have a ratio of 3, 2 to 1. Or if you're looking at a power spectrum, then it should be 9, 4 to 1. That's it. Okay? So if you don't get that, you know you're wrong, but then you should see how well you get that. That's step 1. Step 2 is, let's resum when you're done, when you have your 3 values of omega, capital Y rather, your 3 values of capital Y, let's sum them up to see if they reproduce the input signal. Okay. And when we say sum them up to reproduce the input signal, you certainly should look at it on a graph. Okay? And the normalization may not matter. You should get the normalization right. You can, but at least should reproduce the function very closely. But it should be more than a graph, because the graph can only tell you how good it looks to your eye, which is only a little more than 1 figure, okay, maybe a second decimal place. You want to look at the actual values and see how well you're doing, which gives you an idea of how much error there is in your routine. Okay? So that's always important to do. And likewise, look at what happens when you change the time step. Look at what happens when you independently change the length of the period, and see if they do as you expect. If they do, that means you know the code is working the way you expect it to do. And if they don't, then you know something's wrong. So you do this all the time. My function, your function, make something up as answer you know. Then you should look at the code and say, what if I have a more interesting signal? So here's basically the same signal, omega, 3 omega, 5 omega. So the omega steps are the same. The ratio out front is now slightly different, but you should get those ratios. But now we've added a 7 and we've added a 4. So now see what happens. The 4 should obviously become a DC component. Does your routine output a 4 as a DC? Let's look. Does 7 change anything? Well, it should change something. We have sines and cosines now mixed, so obviously we should get a complex Fourier transform in both cases, but the relative ratios will differ. So this is a good example of, you may want to look at the power spectrum, which combines the real and imaginary parts. So do them both. And finally, I've said this. Okay. Finally, let's get to the physics assessment. Can you remember back where we started? It's a long time ago. We had these 2 functions. We said maybe you or your instructor will tell you which one you should be analyzing. Either a distorted harmonic oscillator that gives anharmonic oscillations, or a very much anharmonic oscillator which begins to look like a square well. Okay. So if you're analyzing the nonlinear perturbed oscillator, this case here, where we can have an oscillation that looks something, say, like that, non-symmetric, about the origin, then you can ask the question, here's the potential, how much of a amplitude must you have? How far from the origin, what x value do you start this off in order to have, say, 10% higher harmonics? Okay? So that's a good question. It's a good question both because it's practical and also you have to understand, you have to interpret what that's asking for. So what one interpretation is, I would say, okay, if we have 10% higher harmonics, that means that the B coefficients or the A coefficients, depending on the conditions, initial conditions, the sum of those should be greater than 10% or equal to 10%. Then we have 10% higher harmonics relative to the lowest coefficient. You may want to say, oh, it should really be in the power spectrum because that's where the power is, and you want 10% power up there. That's what you hear with your ear, power. That's fine. So either one would do. If we wanted to do the highly nonlinear oscillator, I'd say, well, do something like a 12 up here, maybe more, because then this function looks very much like a box. And if it looks very much like a box, then you know it's just going to bounce back and forth and compare the output you get from your DFT to what you got for a sawtooth function. See if they compare. So those are your exercises. Finally, let's quit. We've done enough. It's been a long time. But now you have this valuable tool. We can represent any periodic or non-periodic function with a discrete Fourier transform, or what we'll call for the rest of our lives DFT. Okay? And it's a very nice way of representing functions. Due to the finite measurements, number of measurements, there's certain ambiguities, and that's what I hope you've learned from this lecture, or these lectures, even though you've seen Fourier transforms before. Because an infinite series is not possible on a computer, or because an infinite continuous integral is not possible, we only have finite sums, and that leads to approximations. And that's, that's the limit, but it's also the art of applied mathematics. Okay. Two of the lessons, the rules of thumb you should learn is if you want better high-frequency components, that's obvious. High frequency means little wiggles. If you want to see the fine details, then you have to take measurements at fine little time steps, small values of h, keeping the period the same. If you want a smoother transform, that means, I need a larger t value, so it'll be smooth in momentum space or in frequency space. You can get that by padding, but we warned you about padding. Better to do it by just taking more measurements. Okay. If you want to reduce the likelihood of periodicity of either the function coming back to haunt you, not being accurate, take more measurements. Okay? Nothing beats taking more measurements to get rid of unknowns. Nevertheless, the method is simple, it's elegant, it's used all the time as tremendous power practical applications, and you'll see it again and again. Mathematically, it's a new world. We'll see that when we talk about filters some more, but we're really just rotating from one space to another. You'll do that in quantum mechanics classes. You'll do that in other classes too. It's the same function, just viewed differently. And finally, I recommend, if you have the time, if you're instructed to do it, even if you're not, also look at this lecture coming up shortly on the fast Fourier transform. It's elegant. It's what makes much of the technology we all use now work. But it's more than we have to say here. We've said enough on this. So I'll see you shortly. We'll talk more about Fourier transforms and doing them even better, but you'll use them now for the rest of your life. Good luck. Bye-bye.